Hey everyone, so today I participated in Google Kickstart round A, and so I'm going to talk about my solutions to the problem. And I was able to solve all the four problems. And so I had a final global rank of 123, and I think something close to 30 India rank. I'll start with the problem A. I'll try not to spend a lot of time on A and B. Okay, so I'll also not go through the statement. You can go through it if you want. I'll just quickly explain what the problem is with the test case. So basically, you're given two strings in each test case, and you'll have to check if the first string is a subsequence of second string or not. If it is not, you directly say it's impossible. If it is a subsequence of second string, then you just say how many characters you have to remove from here to get the first string, which if you think about it is nothing but the difference of their size. So this is 5 and this is 4. If you subtract, you get 1, right? All right. So in this problem, I use a standard approach of finding if a string is subsequence of another string or not. I used a two-pointer approach, and based on if the characters are matching or not. So let's say if the two characters match, then I increment both the pointers. Otherwise, I just increment the pointer in the second string. This is very standard approach to check if a string is subsequence of another. And finally, I say an impossible when I'm not able to form the first string from the second one. Otherwise, if I'm able to do that, my answer would be, the size of second string minus the size of first string. Nothing more to this problem. This was a pretty standard subsequence problem. And I was able to solve this in the first 4.5 minutes. So I'll move to the next problem. I'll explain a bit. The problem says that you're given a string. So this string is nothing but a number, and you can append one digit anywhere. Okay, and that digit could be anything from 0 to 9. So you can only append one digit, right? And you cannot append 0 before it because you can't, because it's said here without any leading zeros. So this was the first condition. You can append any digit anywhere in between as well. And second thing is the final resulting number should be a multiple of 9, or rather, you can say 9 should divide that. Same thing. Um, so, so if you know about the divisibility rule of 9, so a number is divisible by 9 when sum of all its digits is divisible by 9, right? Just for an example, like in, let's say, 1, 2, 3, another 3, okay? Or let's take 1, 6, 3 as well. Okay. So sum of all the digits here is 6, 9, it's 18, right? So it's 18. So we know 18 is divisible by 9. So this number will also be divisible by 9. So that's the logic. I mean, if the sum is divisible by 9, the number will also be divisible. So basically, the sum of digits is what we need to find out. So in every test case, we find the sum of digits. In this case, I think it is 7. So we know it's 7, and we can append one character anywhere. Okay, and we want to make sure that this final sum is divisible by 9. Correct. So this digit could be from 0 to 9. So I think the only possibility is to have it equals to 2, right? So this way we can find out what digit we want to, append somewhere. So this is the first part. You find out the digit which you want to append. The second part is where do you want to append it? Um, so the logic behind that is you append that digit, uh, you know, somewhere. So let's say I'll try to give an example. So 1, 2, 3, 4, let's take some 1, 3, 5, 7. So let's say this was the number. You want to append, let's say 4 somewhere. Okay. So I can append 4 here, here. I mean, at any places, right? After 1, before 1, after 3, after 5, or after 7. So there are total of, I think, 5 possibilities there. But we're talking, when we say we want to append 4, and you want to make that final resulting number as small as possible. I think I missed that condition. Yeah, and he wants to construct the smallest such number possible. Uh, so let's say you wanted to append 4 somewhere. If you put 4 anywhere, that number will satisfy the condition. But we want to form the smallest possible number. And the way you do it is you append 4 somewhere. Uh, you know, so you iterate from the left side and you find out the first number which is greater than 4. So in our case, that will be 5, right? So 5 is the first number which is greater than 4. So you'll append 4 just before 5. So this should be our answer, final answer. Yes, so I used the same intention. I'll quickly go over my solution. So I first of all find out what number I need to append. Okay. Then let's say if I want to append 0, I know that 0 is the smallest number, and it's given to us that we cannot append a 0 in the front, right? So the best possibility is you append 0 after the very first character. So you print the first character and then you put a 0 and then you print the rest of the string. So this was actually a corner case since we cannot put a 0 in the beginning. And this is the usual case where you'll find the first character which is greater than C. Okay. And then you just print, substring before that character, and then you print C, and then the rest of the substring. And yeah, sorry for that. And finally, let's say if the character I want to append is greater than actually all the characters, then you just append the character to the last. I just said character, so by character I mean digit. So you append the digit at the last. So that's all about it. This is also a greedy approach, and greedy works here. I'll quickly go to the next problem. So in this problem, you're given a binary string with zeros and ones, and there are some question marks. And each question mark can be replaced with either a 0 or a 1. Now, you want to make sure that the question says that if you can replace these question marks with zeros or ones, and finally ensure that there is no palindrome of length 5 or 5 or more, then you say it is possible. Okay. Otherwise, let's say if you cannot replace these question mark with zeros one in such a way that uh, you'll not have palindromes, then in that case you'll say an impossible. Correct. So for the first test case, it says that it's impossible, and they have shown why it is impossible. You can try to replace. Let's say you put 1, 0, 1 something, but you'll always make a palindrome of length 5 or more. So how do you do this? So the first intuition is when you say a palindrome of length 5 or more. Okay. So let's say a palindrome could be length 5, 6, 7, 8, or more, greater, so on. The first intuition to get here is that, so when you say a palindrome of length 7, what does it mean? Palindrome of length 7, so if I replace, let's say, if I represent some palindrome, it should be something like this. Okay, so since it is a palindrome, you know that the first and last character would be same, right? First and last are same. So if you remove those two, characters, the rest of the string should also be palindrome, right? Because the whole string as a whole was palindrome. So even if you remove the first and last character, this should be a palindrome, correct? So if you think about this, the seven case is actually nothing but a five case. Same is the case for nine. You can eliminate, a nine length palindrome if there is one. You can say that there will definitely be a five length palindrome in that somewhere. Okay, so basically all the odd numbers, they all you can represent using five, because five is the smallest number here. And all the even numbers, you can say similarly that all the even numbers, you can say that they will have a palindrome of six. If there's a one of, let's say 8 or 10 or something, 8, 10, 12 or something, you can say that they'll have a palindrome of length 6. So this was the intuition. You basically what you finally get is you don't have to worry about all the numbers. Just take care of these two numbers, 5 and 6, right? So you just make sure that your whole string doesn't have any palindrome of length 5 or length 6. That's it. So how do you do this? I mean, the way I did this is, so for every character, you maintain a state that what is the last five characters, right? So let's say if I talk about let's say if I talk about zero, this zero. So you'll maintain a state saying this. So these five characters. So this substring. What all are the possible values of this substring, right? So these question marks you can replace with either 0 or 1. So that will give you a lot of possibilities. So basically, in this case, you'll get eight possibilities, two, two, two. So eight possibilities, right? Now, when you append a 0 here, you want to make sure that you eliminate all those possibilities where you're going to get a palindrome by appending the 0, right? So that's the whole intuition here. I'll quickly go through my solution, like what I did. Uh, my solution, I didn't use any bit mask approach. I was simply storing the entire substring. I think most people did it using bit mask. So yeah, I'll quickly go through it. So I have a recursive function you know, which I start from the very end of the string and then I go over, the rest of the characters. Right. So I say that if I reach before this index, I say there was nothing to explore. So I return. If let's say I'm at the first character, so this I treated as my base case. Now the first character could be a question mark. So if it is a question mark, then there are two possibilities of that state. It could be a one, it could be a zero. And if it is not a question mark, you have basically no option. If it was a zero, you append a zero to that state, or if it was a one, you append a one. And so this was my base case. I simply returned from there, right? And then this is my recursive case. So for every position, let's say I'm standing currently at this position, I ask my function to give me answer for this, the previous one, this zeroth one. Okay. So based on what I get from the last state, I now have two conditions. So if my current character is a question mark, so that question mark could be a one or could be a zero. Now I'll try both of these. I'll once try one, then I'll try zero. Okay, so let's say, so I'll loop over all the possibilities I had on the previous index. So basically, let's say for this index, I'll loop over all the possibilities of these five characters. Okay. And I'll append a one there. Okay. So I'll not. So basically, this is not a question mark. So let's take a better example. Let's say for this one, these are five characters, and there's a question mark. So this question mark can be replaced with either a zero or a one. Now I'll loop over all these five characters, all the possibilities, and then see if adding a zero, if I'm not getting a palindrome, then I treat that as a good state, and I store that here, right? So I have a OK method which tells me if adding a one to the end, if that is giving me a palindrome or not. So this OK will return a true when I'm not getting a palindrome. So yeah, this is here I'm handling some just checking palindromes or not. So yeah, I'll do this once with one and once with zero because there was a question mark. And if they are satisfying, then I append those states. And when I say states, so from the previous string, so basically, let's say this was the case. So this was length 5, right? And now I'll append I'll replace my question mark with 1 or 0. So if I since I'm putting one from my position, so I only take four from the previous string. So that's why this, taking at most four characters thing. You'll take only four characters from the previous state and append one character from, from its own side. And finally, I return this, this recursive function returns the answer for the last state. And I just check if the last state had something. So it means that ending here. If I had something, it means there was. It means the recursion gave me some valid permutation till this point, right? So if there was something in the last state, so I'd say possible, otherwise an impossible. Yeah. So this is basically what I did. So this is actually a DP, and then the final problem. So I'll go through the problem. So in every test case, you're given two numbers, A and B. And you have to tell how many of the numbers in this range from A to B satisfies a specific condition. And the condition is the product of digits of number is divisible by sum of its digits, right? So if you think about it, then okay, so let's talk first about the brute force case. So you loop from A to B, and then for every number, you check if that number satisfies this condition or not. Correct? So if number satisfied, you count this, otherwise you don't, and finally you say you just print the final answer. So yeah, that's what my first approach was. I was able to get a partial score on this. So yeah, simply just looped from A to B, had two variables, and then yeah, I was just calculating product and sum by taking one digit from the current number at a time. And yeah, so finally checking if the condition is satisfied, I increment my answer. Otherwise, not. Finally, I print the answer. Yeah, so that's the brute force approach. This will work for 10 power 5, but this will not work for 10 power 12. So yeah, we need to do some optimization here. How we'll do this, we'll see now. So one thing to note that is that, so when you talk about all the numbers till 10 power 12, I think the maximum number you can form with the maximum sum would be something like this, right? 999. This is 12 times. Uh, I'm not sure. Maybe I think this is a number. So this would nothing be but 12 times 9, which is I think 108. So you know that the maximum sum you can form is 108, and minimum sum you know it's 1 only, right? When your number is 1, then in that case your minimum sum is 1. Now, the one thing is clear that the sum of digits of any number would be in this range from 1 to 108, right? And the product would be really large. I mean, the product of digits. Let's say for this one, the product would be 9 power 12, something like that. And 9 power 12 is a really huge number. I don't think you can uh, even do that many number of computation. Not sure in a year maybe. Okay, so what I did was, so for every, so like I've written here, so for every sum, in this range 1 to 108, uh, find how many numbers can have factors of the given sum, which you're right now using, in their prime factors. So I have an example here. So let's say you're currently calculating your answer for sum equal to 12. Okay. So you do this for everyone. Let's say currently we are, computing our answer for 12. Now, 12 you can write as this when you write the prime factors, 2 into 2 into 3. Now, the thing is, you have to find how many numbers can have the factors of this sum. So basically, can have these factors in their product. Maybe I need to correct it in their digits uh, product. Okay, correct. So one. So let's when you say 12. So all these numbers basically are. So if I write these numbers, what are these? 350, 354. 660, 66. Then you have 39 or something, 93, and so on, right? So on. So if you talk about 354, this is the product of digits, 3 into 5 into 4. 66, similarly, like all these numbers, right? So now I want to make sure that, so all these numbers basically have, all these numbers have sum equal to 12. This has 12 sum, this is also 12, 12, and so on. Now, I want to make sure that their product has, 12 in their factor. So if you talk about this number, 354, so 3, there's one factor of 3, which is okay. 5, uh, no, we don't require 5. 4, you have two, so that is 1, 4. So this is a good number. So 354 is actually a good number. Is 66 a good number? No, it's not, because you'll get a 3 here. You'll also get a um, You'll also get a 2 here, and okay, wait a minute. So is this a good number? I think this is a good number. Let's check. Let's check. 60, is 66 a good number? Product of digits is what? 36 divided by sum of digits is what? 12. So it's a good number. Okay, correct. So basically, you have a 3 and you have this 3 in this. So now you're left with a 2 here. You also have a 2, so that 2 is also gone. In this 6, you have a 2. So yeah, this cancels out, so you'll have a 3 remaining. So finally, your this number contains all the factors, right? So this is also a good number. But is this a good number? No, because you don't have these two factors, 2 and 2. Yeah. Same for this. This is also bad. And this is also bad because you'll not have 1, 2 here. So how do you find all these numbers? So this is actually a DP problem. Okay, so before going into actual DP, one thing to note that if you want to find out answer from A to B, let's say, then that would be equal to if you find out from, let's say, 1 to B, and then you find out from 1 to A minus 1, correct? You take a difference of these two, and you'll have your answer for this range. So we're not going to find out for this range actually from 1 to that specific number, right? So that would be our solution. So I'll quickly go over like how I did this. Okay, so yeah, so one important thing, like not sure how this code passed. I think I made a but not sure if this is a mistake or yeah, this works. So it should have been 12 actually, but yeah, this also worked. It should have been, I thought it should have been 12 into 9, but yeah, this also works. I tested it locally also, so 11 works for some reason. Yeah, so you find out the answer from 1 to B, that how many numbers from 1 to B have sum equal to I, And same you do from 1 to a minus 1. How many numbers have sum equal to I? And then finally, your answer will increase by that, x minus y. Now, how I am doing that? So, first of all, I want to. So, this is actually a bit mask. Sorry, not bit mask. This is a digit DP. What do you do is you have a DP. So, what this DP means is that for ith position, the second flag is basically to ensure that your current number is smaller or equal to so far. Okay. And then this is third parameter is basically for uh, what is the remaining what is the remaining factor that should be in your number. Okay. And the last one is what is the remaining sum you need to have in your current number. Right. So, yeah. So, the way I started this is you find out all the digits in this number and push this into a vector. You reverse them. So, basically, let's say if I pass here 123, so this will now be a vector of 1, comma 2, comma 3. Correct? Um, so, yeah. So, that's what I did here. And then I initialize my DP to minus 1. My whole DP is set to minus 1. And then I have a recursive method which is going to calculate this DP, right? So I say that if the remaining sum is negative, it means that I overdid the sum. So my sum should be I, right? My sum should be maximum sum I. So if that exceeds, I return a zero. So there are no possibilities, right? And if I go to the end of the vector, right? So I told 1, comma 2, comma 3 is a vector. So if I go to the end of the vector, I say I check this condition that my this product should be one, the remaining product which I require now should be one, and remainder should be zero. If both of these conditions are satisfied, I return a one. If anyone fails, it will return a zero. And then finally, yeah, you check if the DP is already calculated for that state, you return that value. And this is also like very standard, digit DP. You check if your current state is already small, then you can append. So you can use any digit from 0 to 9. Okay. If it is not, then the maximum you can use is given by your V, which you calculated here. And then finally, you loop over and yeah, recursively call for the next position. And you update your these two things, the remaining sum and the remaining factor you want. So if you're not aware about this technique of digit DP, I'll recommend one blog, I think. So that should be more clear. So there's a blog on Code Forces, I think. Yeah, so this one, I think. This is it. This one. Yeah, so this is the one. So here they are just explaining things, but if you want to go over one code, like how it is actually working, you can take a look at, I think, this one. Check. So this link you can go to. And yeah, so this is one of those very standard problems on digit DP. Uh, if you're not aware of digit DP, I'll highly recommend this blog. Yeah, so that's pretty much about the fourth problem. So the main intuition was this, like if you can get this, you can think of like DP. Yeah, it took me some time to figure it out. It took me, I think, more than like half an hour to figure out this intuition. Yeah, before that, I was searching for some pattern, but there was no pattern. Yeah. So yeah, that's pretty much like the contest. I was able to do it 15 minutes before the end, I think. Had one penalty there. And yeah, that's that I think. So this is so far my second best rank, I think. I had a top 100 rank, something in line of 90s last year. And yeah, that's it. Thanks for watching.